Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this work is all about inferring the support relationships between objects in indoor scenes that we've captured with a Microsoft Kinect. And it's part of a fun collaboration of work that we've been doing with Natan Silverman, my student, Pushmeet here at MSR, and Derek Hoyam at UIC. Okay, so much of the work in scene understanding has been focused on the sort of recognition element. That is, you're trying to take an image and for each pixel, provide a discrete label: wall, picture, floor, table, and so on. But as Derek was saying, this really ignores a lot of information about the scene, for example, the geometry and layout of the room, or the physical relationship between objects. And this is what the latter is what this talk is all about. So why would you care about such things? Well, first of all, if you want to interact with the room at all, if you're a robot and you want to pick up one of the books, you better understand that there's actually a mug sitting on top of it, so you have to move the mug first. And then, of course, you also have the ultimate goal, perhaps, that if you can understand the support relationships well, you could use those to go back and help your object recognition problem. So if you know that there's some objects that's sitting on top of this desk, that dramatically limits the sort of possibilities for what it can be. For example, it's unlikely to be a fridge, and it's more likely to be something that's fairly small and sits, as you've seen before, sitting on top of desks. So what we're shooting for is something like this. You want to take a scene, a complicated indoor scene like this, and you want to understand that the lamp is supported by the nightstand, and the nightstand is supported by the floor, and that the pillows are supported by the bed. Now, what you might just think, well, this would be easy if you had a Kinect. You could just get your depth data and then look at what was beneath each object. Unfortunately, in real indoor scenes, there's an enormous amount of occlusion. So, for example, this little nightstand over here, you just don't see the floor that supports it. Okay? So you have to do some sort of quite complicated reasoning to understand that actually, this piece of ground here is supporting this thing over there. Now, the use of sort of geometric priors, to do this kind of reasoning, we need to use sort of geometric priors about the way scenes work. And there's been a lot of work by Derek and David Forsyth and Varsha Hedau and people like that on doing this kind of task from single views. Perhaps the most closely rated work to our own is this Blocks World Revisited paper of Alyosha, Abhinav Gupta, and Marshall Herbert. So there they use sort of various heuristics based on physical reasoning to try and understand the layout and the sort of volumetric shapes in outdoor scenes. So this work is very much in the same spirit. We're going to be addressing indoor scenes, which are much more complicated and cluttered, but we do have the added advantage, of course, that we have the depth information from the Kinect sensor. Now, to be able to do useful things, we need, of course, a data set of indoor scenes from the Kinect. And in previous work, we introduced a sort of what we're now calling sort of version 1 of the data set, which was a variety of sort of indoor scenes we captured around New York. And we have now a new data set, a sort of version 2 of this, which is bigger in terms of, or it's certainly more diverse. It's actually slightly fewer frames, but each one is much more distinct. One of the problems previously was that all the shots were of essentially these rather cramped Manhattan apartments. And of course, that's not really representative of the way the real world is. So we've got Natan and sent him off to various places around the US. And if you want to capture big indoor scenes with big people's houses, then where better to go than Texas? So we sent Natan off down to Houston, where his parents live. And so many of these shots will be complicated, large indoor rooms with enormous numbers of objects in. So for a small, we captured about 500,000 frames of Kinect data, and then we took essentially from each scene, a small number of distinct views, and it got those densely labeled on Amazon Turk. Okay, and the Turkers, the net result is we have about 30,000 separate objects labeled across about 1,000 classes, and separate instances were labeled. So if you had a table with multiple cups on, each cup instance would have a separate label, which is important for the kind of reasoning that we're going to do. So just to show you some examples. So these are the kinds of shots here. This is living rooms, bedrooms, and so on. This is the raw depth information. We also have a version which is aligned to the RGB image and in-painted to try and fill in some of the holes. And these are then the dense labels provided by the Turkers. So you can see that the scenes are complicated. There's enormous amounts of occlusion. For example, these chairs, you don't really see where, only see the top of them, you don't see the bottom. And then, so it consists essentially of, wide, about this, if you go back to this plot here, this table here, there's about 26 different scene types. So it's, all manner of indoor scenes that you might encounter. Now, because we want to reason about support, just having these recognition, these sort of class labels for the pixels in the scene isn't enough. We also need support labels. So the dataset also has, for each labeled image, these what we're calling support labels, which are essentially saying, for example, for this map, region 2, it is supported by region 3 from behind. So in this case, it's a horizontal support relationship. And then, we also know that region 1 rather, is supported by region 4, the floor, from below. So it's a sort of vertical support relationship. And so we have those densely over the data set as well. Okay, so the particular algorithm I'm going to describe is structured as follows. So our input is going to be an RGB image from the Kinect and a depth map from the Kinect, which has been aligned to the RGB image. And then there's going to be some initial processing phase where we're going to essentially identify the major surfaces in the scene and align them to some canonical reference frame. So we know, for example, what's the floor and what are the walls. And then we're going to do a segmentation to try and discover distinct regions within the scene. And then at that point, we'll then start doing some more sophisticated reasoning about the relationships, the support relationships between those segments to produce the output of the system. So just to go through the pre-processing phases quickly, essentially we're going to assume that there is some sort of orthogonality between the wall and the floor. There's no sort of, we're not in the data center or something like that at MIT. The idea is to sort of essentially take the point cloud we get from the Kinect, fit planes to the major surfaces, and then rotate everything so that the floor is pointing directly upwards. And you might think, well, you could do this automatically with the Kinect's accelerometer. Unfortunately, it's just not sensitive enough. But using the sort of software-based approach, this plane fitting approach, we can actually get about 80% of the scenes to within about 5 degrees of the floor being within 5 degrees, or the normal vector from the floor being within 5 degrees of vertical. There's a small number of scenes for which the floor isn't visible, which makes it much more challenging. So this is why there's still a number of scenes up. There's still a small fraction of scenes for which it's actually quite difficult to get the floor exactly aligned. Now, once we've done that, we then compute superpixels on the scene, like so. And then we're going to use the approach that Derek and others followed in some previous work, which is to take pairs of regions in the segmentation and train a little classifier using the ground truth regions to predict whether we should merge or keep the regions separate. And those are going to be based on lots of features like SIFT computed on each of the regions, or little bag of words, color, and things like that. And so our little merging classifier is going to say which of these regions we think we should combine, and that'll give us then this kind of output here in stage 2. And then we train a second classifier on the segments that arrive at stage 2 in our training set to merge to stage 3, and so on. So this gives us a sort of hierarchical kind of agglomeration of these segments, resulting in, at the end of 5 stages, hopefully we have the sort of fairly large objects all merged into one region. So this process, of course, isn't perfect, and so in some experiments, I'll show you the effect of using these segments we've obtained from the images versus the ground truth segments we've obtained from the Turkers. Now, the major part of the system, of course, is how we do the support classification, and this is quite complicated, and we're going to need to introduce make various assumptions about the way the physical world works in order to make this tractable. So the first assumption up is that we're assuming that each... David? Yes, it is. It uses we have a sort of ablation study where we take out by default we use the depth information from the Kinect, and it does help. If you take, I have a view graphs at the end which we take out different components and you drop it. Yeah. Okay, so the first assumption we're going to make is that each object is supported by a single other object in the world. So we can't have an object can't be supported by 2 separate things. It can only be supported by one thing. And there's a sort of special, the one exception to this is the floor. So the floor isn't supported by anything and can support multiple objects on top of it. The second assumption is that for most of the objects, hopefully there'll be some sort of visible support surface. For example, the deodorant is supported by the sink. But in this image, you can see the floor isn't visible. So we have actually a sort of hidden region, which is really the sort of a hidden floor. So this cabinet is going to be supported by this hidden floor region. And then the third assumption is there's only two types of support that can exist, essentially a sort of vertical support or a horizontal. So that in this case, the deodorant is supported vertically by the sink. And then the other form is that the mirror is supported horizontally, or the mirror is supported by the wall from behind. Now, we don't want to sort of get into the complexities of trying to solve the full recognition problem. So what we're going to do is to take on a slightly easier challenge. And for the purposes of trying to understand the support, it's adequate. We're going to essentially break all the objects into the scene into sort of four structural classes. It's either they're the ground, structure, which really means walls, furniture, large objects in the scene, or props, which are sort of small objects that typically will be interacting in some way with the furniture. And so we're going to build essentially a classifier to predict for each region locally which of these four possibilities that it is. So yeah, in this little color scheme here, we're just showing the typical scene. The floor's in magenta, the chairs are in purple, and the props are in blue, and the walls are in yellow. Okay, so just to set up the formal problem, we've got this scene. We have a set of regions. And so for each region I, we want to try and figure out which is the supporting region. Is it one of the other regions in the scene? Is it the hidden ground or the ground itself? And then, once we've identified which region is doing the supporting, is it supported vertically or horizontally, i.e. from below or behind? And then for each region, is it one of these four structure classes, floor, furniture, prop, or structure? And so the problem is given the image, try and figure out what the optimal assignment for each of these different variables is for each region. So we can take this problem, and it boils down to essentially minimizing a cost function, which has three separate terms. And I'm just going to go through each of these in turn. So essentially, the first two of these are just going to involve local information that we've got from looking at regions or pairs of regions. And then the third term is, in some ways, the much more interesting one, the prior, which is going to encapsulate our sort of geometric understanding of the world.
Rob,
yeah, you can.
So,
yeah.
I guess in the CMU work, they were modelling supported onto the help that 3D reconstruction.
Yeah.
Here you've already got the 3D. I mean, why would you want to model supported ones?
Well, I think the support relationships are quite complicated. So in their world, they're just sort of modeling this building is sitting on this ground plane and stuff like that. In our case, we've got sort of multiple layers of support. So you've got a little book sitting on top of a TV, sitting on top of a table.
I guess the aim in the CMU work was to model support in order to improve that 3D reconstruction.
Right. So,
not really.
Oh.
Right.
It's basically, we didn't really actually do even 3D reconstruction in a classic sense, but it's more was like a segmentation with attributes, like semantic or geometric segmentation. And it's really, you need to understand these pieces to understand the rest of the image. It's not even about the reconstruction. It's really just understanding, right, Rob?
Yeah.
It's without the supports, you're just looking at a bag of floating geometric goo. Right?
So, why is that bad?
Underline Alex's thing. Support is a thing about the world in and of itself. It's not a route to improving reconstruction. If you don't understand support, then you can't answer what will happen when I pick this up. And you have to be able to answer. So it's a thing of itself.
But just a comment, actually, I'm currently working on this, and we can actually show that 3D reconstruction gets much better if you do things like upward gravity and support.
Sure.
You can really quantify that.
Yeah, but I think it's good for many different things. If you understand support better, then you understand the scene better. Once you understand and see that better, you can do prediction, you can do 3D reconstruction, you can do reasoning,
Okay. No, that's fine. So let's just look at the local support. So this is a very simple thing. We're going to take pairs of regions in our scene. We're going to extract a variety of features that capture somehow the relationship between them. For example, the distance between them, the ratio of the bounding boxes. Are they in physical contact, seemingly in 3D? Is one object completely contained by the other when you look from above, and things like that. And we're going to feed those into a classifier, which is then going to come out with one of three predictions. Either they have no relation whatsoever, perhaps region 2 supports region 1 from behind, or it supports it from below. Okay, so just to be clear here, this is a purely local reasoning. Yeah.
So just a question about features here. It seems like this question is not really a question of what regions are like. It's a question of what pieces of contact are like. Right? So it's not really about the book or about the table. It's about the bit where the book touches the table.
Yeah.
And those pieces often have very characteristic appearance in intensity images, and they're kind of hard for rangers to see into. They tend to get the corners wrong. I was surprised not to see sort of intensity features on the edges.
Right, it's true. So there's actually a whole repertoire of features here, and it's possible they might be included. I can't remember exactly if they are not.
In indoor scenes, those cues are often really subtle because you have so much inner reflection, so much light coming from everywhere.
Oh yeah, no.
They're also occluded quite often as well. Often you don't see them as much as you might think.
The information about the support is concentrated sort of in the back rather than on the region.
Right. Okay, so so this is just going to take pairs of regions in the image and give some prediction as to whether it thinks they should be supporting one supporting the other or not. The other local term is going to be the structure classifier. So this is going to be using the sort of standard recognition features, color histograms, SIFT, and so on. And there'll also be some information perhaps about the relative depth in the scene and the height of the region from the floor. And this is going to predict for each region which of the 4 structure classes it is. Okay? And then we come on to the prior. So the prior is going to capture our physical sort of understanding of how scenes work. So the first thing we're going to do is to use those structure classes to define sort of what is plausible. So for these, you can think of as little sort of adjacency matrices or transition matrices. So in other words, if one region is the floor, it can support furniture, props, and structures, but the floor cannot be itself supported by anything else. Okay, this is why this is black here. So white means it's allowed. In practice, of course, I'm showing this as a binary matrix. In practice, of course, what we really do is impose a sort of penalty, a large penalty to the cost if you're in the black in a black square. And then you can see this is for the sort of vertical support relationships. If you have the ones from behind, then essentially a prop can be supported by furniture, another prop, or a structure. But that's the only sort of horizontal support relationship that's allowed. Okay, so the second prior that we use is a pretty simple one. We simply say that, look, if one region is supporting another, it probably is going to be quite close by it physically. So if we're talking about a horizontal relationship, so a horizontal type of support, then we're going to be measuring distance in the XY plane. If it's a vertical type of support, we're going to be measuring distance vertically. Okay, so of course, there are some examples where one object is being supported by something a long way away in the image, but this term would prefer that essentially the supporting object is close by the supported object. We also have a term here which is related to the fact the ground has a sort of special status. So the ground itself doesn't require any support, but that can only be true if the region in question is actually labeled by the structure prediction as being of the floor class. Okay, so you can't be a prop. A prop must have support, but if it's labeled as ground, it's okay not to have any other region supporting it. And then the final term in the prior is essentially a sort of global consistency term for the ground. That is that all the regions that we think might be ground, they must have the same vertical height. Okay, so if we've done that initial alignment phase correctly, we can then do some things like, for example, this book that's lying on the ground, it's got a slightly different height to the surrounding region, so we know it can't be part of the ground. So therefore, it must be a prop instead. Okay, so we take this big energy and essentially formulate it as an integer program. So it actually turns out to be a pretty big integer program because we have to sort of come up with variables for all of the different regions in the image, and then coding these interactions between the regions makes it also a bit bigger as well. So to solve it, we relax it into a linear program and just throw it into MATLAB's linprog. Okay, so that's the overall approach. So let's look at some experiments now. So
then some of the physical constraints might not be. I mean, there are some hard constraints. I thought all of them were hard.
Well, in practice, I think so.
With the linear program, you can get some intermediate.
Yeah, in practice, there are sort of very large constants in there.
Yeah, but with linear programming, you might get in trouble, right? Because you get out half correct physical
That's an interesting question.
I mean, you can always route the empty solution to get the...
Yeah, but it might not be physically.
Yeah, it's true that we haven't gone. There certainly might be cases in the results where things are physically implausible, but I'll show you them in a moment. Most of them tend to come out. There is some rationale behind the prediction it provides. Don't seem to be too many physically implausible things happening. Sure.
Is there a reason we are not using the structure of the molecular model? Here you're just treating as a black box linear curve. Why not using the IUS? Most of your terms are pairwise, right? So why not just using the standard inferencing model?
I think it's because a lot of these let's see. So I think a lot of it has become because you actually want to have a single assignment for each region. So you really want to, and there are also sort of exclusion relationships as well, so that once one region becomes the floor, the others, nothing else can be the floor. So those kinds of things would be essentially these sort of higher order cliques in the MRF, which might be hard to code, things like that. Although admittedly, there are some fancy MRF techniques from Pushmeet and others that might be able to do such things. Okay, so now in terms of the experiments, we need to have some baselines here. So the first thing to say is that the first approach is that we essentially use our full classifier to determine the floor, and then we do the dumb... David?
So, Rob, I'm wondering if that matters. So there's a sort of really interesting question about support here. Here, getting short local chains of support right all the time really matters.
Right.
But having kind of global physical consistency seems like a sweat. And what it's really telling you is you can look at some really big tower of bricks and tell which ones you can pull out and which ones you can't. And that's not consistent with my own experience and my own reasoning about support.
Okay, so first of all, so in these baselines, we'll have baselines which consist purely of local reasoning, and then I'll show that they don't work quite as well as if you bring in the sort of more global reasoning for these scenes. Okay, so for example, this first baseline, you can do the dumb thing, which is to just look down from above and see what's underneath the region, and that would be the supporting region. Okay, so that's a sort of very local prediction there. And then if you're sort of looking at horizontal support, you'd look for this red region being sort of enclosed on as much as possible by this region behind it. And if that's the case, then you say, okay, that red region is supported by the orange region. Okay, so that's just using somehow the information we get from the Kinect in the simplest possible fashion. The second baseline also brings in this local structure classifier. So now we have information. We run a little structure classifier, and if we predict structure or furniture, then you just assume it's automatically supported by the closest floor region. Okay? And then the props, that is the smaller objects in the image, you're going to use the previous idea, just looking from above to see what the object is directly beneath it. So again, so this one essentially has all the information from the first two terms in our cost, but doesn't have the prior terms, which encode the more global constraints about what is possible. And then for the final baseline is essentially just to use local information from the support classifier. So that's the one that took pairs of regions, made a prediction about whether they should be supporting the other or not. Okay, so in this little bar chart, we're first of all going to start off using the ground truth regions that the Turk has provided. Okay, so this is not using the segmentation pipeline that I described. This is the sort of gold standard. This is the best we could possibly achieve in our support reasoning. So the first three sets of bars here are the baselines, and the last one is our approach here. So what you can see is that the blue bars are where you don't care about the support type. That is, you've correctly identified that the chair is being supported by the ground, but you didn't figure out, you don't care whether it was a vertical support relation or a horizontal support relation. The red one is when you say, okay, now I do care whether it's a horizontal or vertical type of support. So you can see when you care about the type of support, the performance does drop. This one here is the one which just uses the sort of local information in our cost function and doesn't use the priors. So you can see it does pretty well here if you don't care about the type of support, but if you do care about it, the performance drops. But once you bring in the priors, which will do this more long-range reasoning, then you do see a sort of reasonably significant jump in performance there. Now, of course, this was using the sort of gold standard regions. What we'd like to do is to in fact, use the regions we produce automatically. So this is the performance, this is what the bar charts look like. So all the numbers drop. If you look at the y-axis here, the numbers drop a fair amount, but the overall trends remain the same. Again, you'll see this interesting thing where if you don't care about whether it's a horizontal or vertical support you predict, you do almost as well as our overall scheme, but if you do want to correctly understand whether it was supported from below or from behind, the performance does drop without the sort of the prior information in our model. Okay, so this is just showing you side by side the performance of our overall approach on the ground truth segments and then the segments produced automatically. So just to finish up, I'll just show you some examples. So this diagram's a little bit complicated. So here's the image from the Kinect of, in this case, some office scene. On the right, the colors show the different outputs of the structured class classifier. So it correctly figured out that the floor was this thing in pink, the major pieces of furniture in purple. This monitor was incorrectly thought of as a piece of furniture, which is why it's in this funny hashed thing indicating incorrect structural class prediction. And then the arrows indicate the predicted support relationships. So if it's red, we got it wrong. If it's green, we got it right. And then the circular terminator shows the horizontal support that is supported from behind, and the green one shows support from below. So for example, we got this lamp wrong. So here's the lamp. You can't see the base of it. It thought it was attached to the wall. Okay? That's incorrect. Then you can take something like this fridge, or I think it's a fridge sitting over here, or a cabinet of some type. This was correctly reasoned that it was supported by the floor over here. So that there's this whole segment was essentially the chair, so there was a tiny piece of floor underneath, but it didn't use that when it was making that prediction. So you can see that there's and then you can see also, for example, this thing sitting on top of the microwave. It understood that the microwave was doing the supporting there, but then it got confused and thought the microwave was somehow attached to the wall, this is why this is in red. Here's another scene, a sort of desk. So it understands that you've got objects on desks, which then the desk is then supported by the floor, and you can see that it thinks this lamp, which is you can only see the sort of head of the lamp. And it can't see anything underneath it, so therefore it thought that was supported by the window, which is not unreasonable, given that the rest of the lamp is completely occluded. So this is using the ground truth regions. Of course, things are going to look nicer. Now let's swap to the automatically generated regions. So here we can see a bathroom scene. There's a little alcove here. In this case, it thinks that these little shampoo bottles are supported by the wall. It does figure out, though, that these ones are supported by the bathtub. In this case, there's no ground plane visible, so the technique would have been essentially using that hidden ground region to do the reasoning. And then this is a kitchen scene, so you can see here it's getting most of the things right. It thinks the sink is supported directly by the floor, which I guess it's a bit of a debate exactly what is supporting the sink. I suppose technically it's the countertop. But you can see here it's getting most of the support class classifiers broadly understanding that these are sort of small objects sitting on some large piece of furniture, and it is this plate. It's reasonable to assume that it's supported by the countertop. In fact, it's sitting in the dish rack, which of course is a fairly small and non-visible object. So it's not unreasonable that it's got that one wrong. David, yeah.
So there's a really interesting question of how you keep score with the loss function. Okay? If you think about your shampoo bottles that were in an alcove that they were declared as being supported by the wall, you could very reasonably argue that basically just doesn't matter. You've got a fairly good idea of what's going on, and you refine your grasp of the last time and everything that's going on. You've got a theory of that.
Yeah, it's a good point. I mean, in this case, we just we wanted to keep things simple, that we just had a sort of binary thing.
It's very hard to be shocked or distressed by that.
Yeah, that's a tricky. Yes, it's a good question. I'm not quite sure how to do that. I mean, the same thing arises in any kind of hard categorization problem. I mean, you have to quantize to some sort of label set.
So a follow-on question.
Sure.
Imagine I insert a class unsupported, which is a really interesting class because it identifies projectiles. So a ball flying through the air, that sort of thing, and I care about projectiles because they're interesting. Now the danger with unsupported is that the classifiers will run amok and classify everything as unsupported, and I'll bite the dust. Do you have any intuition about what would happen with the current system?
Yes, I think it would go crazy. So I think it was a very strong constraint that you only had one region being unsupported, i.e. the floor. and that this constraint that every other region must be supported by another one was pretty critical, yeah, I think.
It would be very attractive
Yeah,
to say,
yeah, I think Natan did try this actually, and it's all chaos ensued. So I'll just wrap up because Derek's showing things in me. Okay, so what we talked about here is essentially the support reasoning for indoor scenes. They're really difficult because of all this occlusion going on, and they're genuinely complicated interactions between the different objects. In this work, we haven't closed the loop somehow and used our support reasoning to go back and try and improve our identification of the objects. We'd like to try and do that, something we're working on. And I encourage everybody, if you're interested in our data set, it's freely available online, and it's hopefully do let us know if there's any problems with it. We'd be very willing to fix it.